What's your metabotype? You can run, you can swim, you can walk, and be as active as you deem necessary. And all of that is important. How effective is that to you? Everyone is different. We have established that by now. But these differences can be characterized into types, also known as metabotypes. Right now, we're going to be looking at some literature and the metabotype concept. Some of the research papers that we're going to be reviewing include Paving the Way to Precision Nutrition through Metabolomics, Perspective, Metabotyping, Potential Personalized Nutrition Strategy for Precision Prevention of Cardiometabolic Diseases, and the third one will be Evaluation of Metabotype Concept Identified in an Irish Population in German Core Cohort Study. Now, let's get on to the first research paper. This first paper was the first on the chronological timescale, with its publication dating back to 2019. The key ideas reflect on slowly progressing the metabotype concepts problem and outside influences. Food patterns and eating behaviors are extremely complex. They include multi-layer informational flows. Similarly, gene-diet interactions might play a role in the development and protection against chronic diseases. For example, the Mediterranean diet's antioxidant content could provide a protective mechanism as antioxidants modulate gene expression. Different studies confirm the complex interactions that exist among food components, dietary patterns, and epigenetic modifications. In this paper, it is reported the strong influences genetic variants have on metabotypes. This idea, cited further in the paper, explains the interconnection present between metabolomics and gene regulation through epigenetics. This idea confirms that integrating metabolomics and other omics might be of great interest to future biomarker plus metabotype researchers. Given this biological complexity, systematically tracking relationships between diseases through multi-omic lenses is very challenging. So innovative systematic strategies are urgently needed to unveil the role of metabotypes in disease development. Ultimately, design dietary recommendations to promote health and well-being or cure diseases. Now let's move on to the second paper. This paper was the second in the chronological timescale, with its publication dating back to 2020. The key ideas reflect on identifying what's preventing metabotypes from progressing, going on from a new concept to the concept in cardiometabolic precision prevention. Metabotyping is a relatively new concept with the area of precision medicine. In current literature, like the paper previously mentioned, metabotypes are often defined as either based on clinical and anthropometric body measurements, markers, disease-associated metabotypes, or the metabolism of certain nutritions and dietary components, such as dietary fiber and polyphenols, diet-associated metabotypes. Rather than looking at the metabotypes as two diverging subfields, what if we looked at them as a big picture? What if disease-associated metabotypes, that is, metabotypes present in those populations at high risk for cardiometabolic diseases, will affect the response to a specific diet? Gut microbiome is a crucial determinant and a modifier of metabotypes, as well as habitual diet, phenotype, anthropometric methods, biochemicals, and clinical markers. In other words, the interaction between the host, you, and exogenous measures, e.g. diets and drugs, and gut microbiome is a crucial factor in dietary response and identifying certain metabotypes. Very few studies have been reported in which metabolomics has been applied to metatyping as a way of developing enhanced strategies to combat cardiometabolic diseases. These studies have grouped males and females into metabotype-delivered classes associated with disease characteristics. Study 1. Men and women from a large Irish study, for example, were grouped according to their plasma fatty acid profile, introducing 4 groups that varied in terms of metabolic syndrome components, anthropometric indicators, dietary habits, and demographics. More on this later. Study 2. Another study, urinary metabolites associated with diabetes were used to separate diabetic and non-diabetic patients into 4 novel classes. The variations in plasma glucose levels led the authors to speculate on the differences in metabotypes, diabetes control, and the potential possibility of complications for the 2 metabotypes in a diabetic patients. Study 3. In another recent study, 2 distinct subgroups of monozygotic twin pairs were associated with cardiometabolic risk factors, high-density lipoprotein cholesterol, and BMI were identified using metabolomic agents, aka metabotypes. This paper was the third on the chronological timescale, with its publication dating back to early 2020. The key ideas reflect on evaluating and studying the German Core Cohort Study, specifically the Irish population. Additionally, one of the reasons I tried to incorporate this paper is that it is merely factual data, so it has required me to do most of the analysis and comprehension. Using data gathered from these studies, we could identify groups most likely to get certain diseases. This way, we could red flag high-risk population groups and provide them with the most practical prevention measures. Considering that groups in different dietary patterns, the vision is to develop a complete customized prevention model with relatively dietary changes. However, further validation and recognition of differences in lifestyle disease associations between metabotypes is vital and crucial for creating targeted disease prevention strategies. See the image above for examples of identifying high-risk groups. Separated by the 3 clusters in the study participants, this is how the study participants were separated. Pay close attention to the 3rd cluster, as most of the inactives and smokers were placed there. This table shows the total study population's demographic characteristics and of each of the 3 metabotypes clustered identifying the core F and FF4 study. The study population aged 32 to 77 years comprised nearly equal populations of men and women. They were separated into 3 clusters, groups of metabotypes. Of 1,744 participants, 590, 33.8% were assigned to cluster 1, 813, 46.6% to cluster 2, and 341, the inactive cluster, to cluster 3, 19.6%. The proportion of men was higher in clusters 2 and 3 compared to cluster 1. Cluster 3 was categorized as the cluster with the highest median range of 62 years and BMI of 29.7 kilograms, as well as the highest proportion of physically inactive individuals and smokers. In other words, the most populated cluster, cluster 3, had the highest percentage of individuals physically inactive and smokers, while the first 2 clusters had minimal amounts. One of the biggest challenges we are facing in metabotyping is the fact that we all lead such different lifestyles. There are many inevitable changes that have to happen and are going to happen before we push metabotyping into the clinical settings. But the biggest one is the fact that everyone is so different in terms of lifestyle, like nutrition, physical activity, and etc. The above image here depicts this perfectly. Determinants like diet, education, environment, genes, lifestyle, medication, and gut microbiome influence metabotypes. And if we don't have a correct analysis of the correct metabotype, how do we apply it to real people in cardiometabolic settings? Let's look at this like an analogy. Picture yourself working on, let's say, a biology project that's due in a few days. You have due date stress. Your younger sibling comes into the room and nags you to play with them. 5 minutes later, another sibling comes into the room and nags you to play with them again. Once more, 15 minutes later, let's say a cousin comes into your room and nags you to play with them. You understand what would happen. This is a continuous process of stress and confusion. They would continually pressure you and stress you. The environment around you would feel stressful, aka your house in this case. It would continuously pressure and confuse you. Well, you aren't the only one that feels this. Biomarkers and the factors of metabotyping and general metabotyping experience this too. And that is why lifestyle is such a big aspect of the challenges. There are so many influences. The lack of foundations creates lack of stability. And how are you supposed to ensure that you can push this concept forward and use it in cardiometabolic settings when you aren't even sure if your study and results are correct? How do we progress on this? Going forward with metabotyping in the future will require fresh, new perspectives, a fresh pair of eyes, let's say. But to do this and to drive down this road, we need to set a strong theoretical foundation. Also, evidence for the cost effectiveness of well-designed international studies is also needed. Now, it comes into play the idea of putting this imaginative-like idea into the real world. Although it seems impossible to fill in the wide context gaps in metabotyping, it isn't. It isn't impossible. It just requires a different kind of approach. It requires an unconventional approach. The context gaps must be filled by multidisciplinary teams of clinicians, biomedical scientists, computer scientists, nutritionists, and behavioral psychologists, as well as the coming together of the omics family, aka transcriptomics, proteomics, genomics, metabolomics, and etc. Like the clusters of metabotypes, the scientific community must come together to drive down this now pothole-full road, but in the future, smooth, clear, and bright road toward predicting and preventing cardiometabolomic diseases.